Today I'm going to teach you about the remainder theorem, and the remainder theorem is quite useful in trying to find the remainder of dividing a polynomial by a binomial without actually carrying out any type of long division or synthetic division. So let's start with the definition here. The remainder theorem states that when a polynomial function p of x is divided by a binomial of the form x minus a, the remainder is equal to p of a. Now this a value is the root of x minus a. So if you plug in the root of the binomial, in this case the divisor, you get the remainder. So let's actually put this into play here. Let's look at the first example. Without using division, determine the remainder when p of x is divided by x minus 2. And then verify that solution using synthetic division. So the first step in applying the remainder theorem is to find the root of this divisor. So find the root of the divisor, set it equal to 0, and solve for x. So the root of the divisor is 2. Then, to find the remainder, you want to find the value of p of 2. So wherever you see an x in your polynomial, which is right there, you're going to plug in a 2, and then you're going to evaluate. So let's plug in the 2. 2 cubed minus 4 times 2 squared plus 2 times 2 plus 5. So let's do some simplification here. 2 cubed gives me an 8. Negative 4 times 2 squared gives me a negative 16. Plus 2 times 2, which is 4. And finally, plus a 5. Let's keep going. 8 minus 16 gives me a negative 8. 4 plus 5 gives me a 9. And we are super close here. Finally, p of 2, or in this case, the remainder is going to be negative 8 plus 9, which is 1. So that is the remainder when I divide p of x by x minus 2. So you don't have to do any of that synthetic division if you ever need to find a remainder. But if you want to check your answer here, we can actually just carry out the division. So set up your synthetic division as follows. You got the upside down division bar. What goes inside are the coefficients of your polynomial. It looks like we don't have any missing terms. Everything is in descending order by degree. So my coefficients are 1, negative 4, positive 2, and positive 5. And what goes in front is, of course, your root of your divisor, which is 2. So bring down the 1. 1 times 2 is 2. Negative 4 plus 2 gives me a negative 2. Negative 2 times the 2 gives me a negative 4. 2 minus 4 gives me negative 2. Finally, negative 2 times positive 2 gives me negative 4. And once you add these numbers, you get a remainder of 1, which confirms what we got over here using the remainder theorem. So it's kind of neat. You don't need to do all that division to find the remainder. You can just use the remainder theorem. Let's take a look at another example here. It's a little more complicated. Without using division, determine the remainder when p of x is divided by x plus 5 this time. So we have more terms to work with. So if you don't want to carry out the division, you've used the remainder theorem. So find the root of your divisor. X plus 5 is equal to 0. And your root will be negative 5. Now, to find the remainder, all you need to do is find the value of p of negative 5. So wherever you see an x in your function, you plug in a negative 5. So let's do that. Negative times, or negative 5 to the power of 4 plus 7 times negative 5 cubed minus negative 5 squared plus 2 times negative 5 and lastly negative or minus an 18. And we want to find the value of this whole equation here. Now we're working with bigger numbers here, so you have to be a little careful when you're calculating this. So a negative 5 to the power of 4 gives me a value of negative 625. The next term is going to be minus 875. And this negative 5 squared gives me a minus 25. And 2 times negative 5 gives me a negative 10. And negative 18 stays the same. So if I do this correctly in my calculator and add it all up, you get a value of negative 1,553. Now that is the remainder when you divide p of x by x plus 5. Okay, and I got another example here, one step further. When p of x is divided by x plus 2, the remainder is negative 18. What is the value of k? So in this case, they give you the remainder, they give you the divisor, and they give you the polynomial, but the value of k corresponds to one of the coefficients of the polynomial, and that's what we're going to try to find here using the remainder theorem. So find the root of your divisor, equate it to 0, and solve for x. So our root is negative 2. Now I want you to read the question again, take a look at the information that they give you. They give you the fact that when you divide by this binomial, you get a remainder of of negative 18. Using the remainder theorem, that means p of negative 2 is negative 18. So you're going to use this relationship right here to find the missing value of k. So how do we do that? I will show that right now. Let's actually take your function. Wherever you see an x, you plug in a negative 2. So negative 2 to the power of 5 is the first term. Minus 7 times negative 5 squared. Oh, not negative 5. Sorry about that. Should be negative 2 squared plus a k, which is what we are trying to find, times negative 2 plus 10, and this is going to be equal to a remainder of negative 18. So we have an equation here. The only thing that we don't know and what we want to find is k. So let's go ahead and try to find that. So negative 2 to the power of 5 is going to give me a negative 32. Negative 7 times negative 4 squared is the same thing as negative 7 times positive 4, which is negative 28, plus k times negative 2. Now I'm going to fix it up, make it look a little nicer. Put the 2 in front. Negative 2 times k plus 10 is equal to negative 18. Let's simplify even more. If I put together my like terms here, I'm going to get a value of negative 50 minus a 2k equals negative 18. From here, you want to you want to add 50 to both sides, and your result is going to be negative 2k, because these go away, and negative 18 plus 50 is going to be a positive 32. Last step is divide by negative 2, and I finally get a value of k, which is negative 16. And that's how you apply the remainder theorem.